the power that is power reflect from the input port of the network, or the power available from the Z0 minus the power that has been delivered to the Z0. Similar concept for the output. You have the A2, which is the voltage waves entering your output of the device. If you take the absolute value squared, you have the power of those of that value, and you define that as the power that is incident into the output of the network. And obviously, if you have a power amplifier, you don't have power that's incident in your output of your network. You want that power to be, you want B2 to be large and A2 to be small. And in the other way, you want A1 to be large and B1 to be small. So you want a lot of power to be entering in and a lot of power to be entering out of your system. The power that is entering from the output of your system, that is the A2, which is the power incident on the output of the network, or the reflected from the load, so that the load and the output of your network don't match. If your power amplifier is connected to an antenna and that doesn't match with respect to the input of the antenna, then you will have that power will not just be lost into the conductor, will not start to have a, if you start to have a voltage standing wave there, then you have a problem because you will have an output oscillation. But what is going to happen is that your device is going to shoot a lot of power towards the antenna. The antenna will not accept most of it. A lot of it will be dissipated through the conductor, but a lot will be reflected back into your amplifier. And what does that do? It causes a voltage hoop at your output of your amplifier, and that voltage hoop can transfer your change the current that you draw. It transfers the state that you're in of your amplifier, which means that you might see points where your device is not stable, and you don't know how long that your device will be able to sustain such high current, high voltage hoops at the output until it breaks down, until so much of the output power is being transferred back that it enters compression, and at some point in compression it will enter breakdown. And that's very important to know these relationships between I have a source, how well is my input matched, how much of the power is going in, incident into the input, how much power is being reflected back, how much power is coming from my device, and how much is getting rejected from the load. Relationships of these give you the output power and the input power. The output power is basically B2. That's why we want to have large. We want this power towards the power that is being accepted by the load, by the antenna. The power amplifier, I attach it to my antenna. As much as the power is being accepted, I want that to be maximized. That is my B2. My B2 is subtracted with A2, which is the power that is reflected back from the antenna that the antenna did not accept. And that's the P out. The P in is basically the power that I'm driving in versus the power that's getting reflected back from my amplifier. So before even my antenna, there's an amplifier. I'm trying to feed my amplifier so that it amplifies the signal, but it seems that some of the signal is getting reflected back. And this power input is basically how much I was able to push in minus that what came out. And the subtraction, and why is it subtraction? Because we're working in dB here. We're working 10 log base 10 to the milliwatt value divided by I think there's a divided by 1 milliwatt. So we're working in dB, which means we can just say P out minus P in. We were in absolute values, we would say P out divided by P in. The gain of the device, if you have an amplifier power device, you say, hey, this device has this gain because what do we say with gain? We say the power that I drove in, which is the total power I had, minus the power that got reflected back, minus the power that I got out, and which is the total power that got out minus the power that got reflected back into the output. So P out minus P in will give you the gain. The gain is in dB. The power is in dBm with reference to milliwatt. dBW is with reference to a watt, but we usually work in dBm. In RF, yes, in the lower bands you do have mega. You can even generate ranges of kilowatts, but usually at 100 gigahertz or so forth, you will not have. You will always be in terminal talking about milliwatts, and that's why the reference is with respect to milliwatts. It's the closest unit value that you can have a reasonable comparison to, and the difference of them is in dB. So you say, what is the gain? Gain is always in dB. Power is always a nice. It's always in watts because it is It is reference to a unit of power, which is watt, milliwatt in this case. This is now a characteristic of, I think I showed you also in ADS last time when I showed you the Doherty. Do you remember the Doherty? If you don't, go to the last week's recording. I will be uploading that together with this week's recording. The Doherty is an amplifier which consists of two parallel amplifiers that are biased in different classes, and we'll go also to classes in this subject. And that they are trying to increase the efficiency. So what is the power efficiency? And we saw that the Doherty had this like curve, this weird curve, which was big here, and then they had a little slump, and then it got bigger again, and then it went back. And the curve was underneath the depicted input power and then the efficiency. Here we can see a similar curve. We have input power to the horizontal axis and the two vertical axes. One is depicting the gain and the output power, and the other one is depicting the efficiency, the PAE. PAE, what is PAE? It's the power added efficiency. It is the efficiency of the device that takes into account the DC power that you're putting in. So it's the power efficiency, but it also takes into account not only P out versus P in, not only your F power, but also your DC power that comes in. Because that's very important to take that into account, as you will be, as it will definitely lower because the device in itself also has thermal losses. So a lot of your applied DC power at the drain source voltage will be dissipated into heat. We discussed it beforehand. Heat is a problem. Heat is managed via packaging, and the packaging, whether it is flip chip or whether it is on the submount, it's always a question of heat dissipation. Here we have plotted three parameters. As I said, the output power, the gain, and the power added efficiency. The power added efficiency is this curve that goes linearly and then starts to saturate in the upper part. That's the one that depicted in circles. And we can see that the efficiency of the power device is being measured in three different voltage points: at 25 volts, at 30 volts, and at 35 volts. And what can we see? Well, the device seems to have a higher efficiency when you apply higher voltage. But you cannot unendingly apply higher voltage. Applying at some point, the voltage will be high, even too high for a power device, that the power device will have the similar problems of a device which is a lower bandgap device, where it starts to burn. But a rule of thumb, higher voltage, higher efficiency in this case. This efficiency curve, this lower efficiency at the low input power, and then as you increase your input power, you're increasing the gate voltage because you're increasing the hoop of your input voltage signal. So you have a sinusoid signal that you're driving in. You're increasing the hoop as you're increasing the power. You're increasing the swing of the input voltage. This will obviously drive your device more into saturation. The higher you drive your device into saturation, the more efficient device you will have. And the more you back off, that they call the terminal at back off, the more you move away from the saturation point, the more your device is linear. That's why all the characteristics are, the gain is consistent. If a linear gain means that the gain is consistent. Basically, whatever we're changing into the gate, the drain current is remaining the same. So the gate, the gain remains flat. The gain here is depicted with the triangles. You see the gain in the lower part, where the input is low, the gain is flat across of it. It remains flat. For 16, for 18, for 20 dBm input power, the gain is flat. The device is constantly producing the same amount of gain. That means that your device is behaving in the sense it still hasn't entered saturation, it's behaving linearly. So it's providing you with a continuous gain towards from what you put your input and what you get from your output. But the issue there is that that's fine and good. However, at those points, we're not getting the amount of power we want. We're designing power devices, so we want a lot of power. In those cases, we're getting low power, and we're getting also very low efficiency, which means that a lot of the DC power that we're putting in this device is getting burned out. So you have you have an amplifier which you want to amplify 16 dBm into 28 dBm, so let's say 10 dB difference. You want the device to give you this 10 dB difference, but at the same time, your device is working with 2% of efficiency. So it means that 98% of the power that you're giving to is getting lost. That is insane. You can't operate the device like that because it will start to burn. That's why your loss will be simply too high. And even if the device doesn't burn, your loss is simply too high. Doesn't make sense to design. So you want an amplifier which has a high amplification. In order to have a high amplification, you want a power amplifier that has a high voltage. Having a high voltage means you have a high efficiency because you're having also high input drive. And when moving to the right, when moving a high input drive, high voltage, you can see that all the linear part, increase of the linear part enters saturation of the output power, enters saturation. At some point, it starts to enter compression and then to break down. So that's the behavior. And we wanted to design there, the saturation part. We want to design there where we've exited the linearity aspect and we've entered into the aspect where our input power towards the output power diverges then into 1 dB output point and then also a 3 dB output point. At 3 dB compression, where we start to then have this saturation and then the fall at 3 dB compression or 1 dB or 3 dB compression depending on how many harmonics we want, and the terminus is harmonics. And we will see that in the next slide. Why harmonics? We designed the amplifier, so we wanted that point over there. You know, we're driving a certain amount of power in, and we have it there. Meaning that for a power device, higher voltage, higher output voltage, higher input drive means a higher efficiency. It means a higher output power, and the curve starts to the gain curve is not in this flat area. It is not in the area where it is linear, but it's starting to enter compression. And then the entering of the compression point is usually you measure it. Okay, then being linear, and then I'm entering compression, and then you have here where you enter compression. As you measure how much the difference is from your maximum point. Is it 1 dB? Is it 3 dB? Because this 1 dB or 3 dB here will be reference to how much output power you have there. As high of an output power as possible, because you're designing a power device. You want power from this device, nothing else. Power, in this case, why we were able to say output power was, or the gain was P out minus P in, the gain was divided in dB. We're taking these milliwatts and we're transferring them into dB scale. And I think probably you've been familiarized with this, how that works in the 10 log 10 scale. 10 log base 10 to then your X, which is your milliwatts for your power. And how that transfers as 0 dBm means 1 milliwatt, 10 dBm means 10 milliwatt, and then, for example, 13 dBm means 20 milliwatt. That's an increase of 3 dB is times 2, an increase of 10 dB is 8 times 10. For example, in this case, an increase 10 dBm was, 0 dBm is 1 milliwatt. If you say 3 dBm, how many milliwatt would that be? If 3 dB is an increase of 2? Any answers? 2 milliwatts, yeah. So, and then what would be 6 dB? Four milliwatts. And so forth. So in this scale, you have then 10 dBm is 10 milliwatts. If you want to have 20 milliwatts, you have 13 dBm. But if you want to have 100 milliwatts, you have times 10. So if you want a factor of times 10 in the milliwatt scale and a factor of 2 in the dB scale. So you have from 10, you move to 20 dB. 40 dB, 10 watts, and so forth. So it's easier to, in the dB scale, to then, why is it easier? Because it allows you to move from multiplication and division into addition and subtraction. And if you have these two-port devices, these chunks, you're not designing only one two-port device. You're designing multiple two-port devices, and we're going to be talking about decoupling, DC coupling capacitors as well, because you're designing these multiple chains. You don't have only one transistor finger, you have multiple transistor fingers in parallel as well, and besides in parallel, next one after the other in a daisy chain, because you can't always just shove a huge amount of power and expect that huge amount of power to be amplified by the transistor. No, the transistor at some point will burn down. So you have a low amount of power, and with multiple steps, you go from amplifying it in chunks to a high output power. Either that, or you have the problem that you have a low gain at the operating frequencies that you're designing an amplifier, so you have to have more of these chunks next to each other. In CMOS, for example, CMOS is also nowadays used for high frequency. It's not that only silicon carbide or whatever. Even standard CMOS is used for CMOS and for RF and high power as well. And what they do is that they have a ridiculous amount of transistors that are just daisy chain in series to each other, so in order to achieve the required output power at the frequency point. So it's a very large amount of transistors that are just either parallelized and then in series to each other. And this principle is followed also here. And you're doing it in chunks. And when you have one transistor is a two-port device, another transistor is a two-port device, another transistor is a two-port device, so you have all these two-port devices, and in order to make it easier for you to just add up the gains, not to have multiplication, blah, 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 we talk in dB then. And dB allows you to just add up those. Power added efficiency, why is it important? Well, power added efficiency is also one of the parameters you should remember for the exam, drain efficiency and total efficiency. Very good to remember all of these and to know what they mean. The power added efficiency, we plotted it there in the previous two slides. You can see that the one that goes from low to high then. In the, what is power added efficiency? These like circles. In the circular artifacts, whatever, symbols. That is the output power of your device that's generated, amplified, minus the input power that you drove in, divided by the DC power. So what shouldn't be forgotten, because you can have the drain efficiency, and the drain efficiency is usually very good. If the power added efficiency is 60%, the drain efficiency is 75%. Because you're not taking into account the amount of DC losses that you're having. Because your DC losses, your device is, obviously as we can see here, every device has losses. And also these active devices have losses in them. And if you don't take into account these losses that you have to drive the device, it is very it is cheating in a way if you just take the drain efficiency, because you have to consider the input power and the input power that you drove in, and you have to consider the DC power that you spent to drive this device. The total efficiency is then defined over the P output or the P input over plus the DC power. So there's different ways of defining efficiency. The primary way which we use in amplifier design is the PAE, the power added efficiency. But all these three are good to know for the exam. Now, you want to design an amplifier. That's fine. You saw I showed you I think beforehand you've also seen small signal approximations of the transistor model. And you've seen, I've shown you where you simulate the matching networks, you simulate the input, the output, the reflection coefficients you try to adjust, all fine, but I've never shown you the transistor finger in itself. So obviously the transistor finger has to have a model to it. So it doesn't just, you're not operating it in this scale, so you're not operating it here in the lower part where it is linear, where it's behaving linearly, but you're operating it at the part where it's behaving non-linearly, where it's trying to compress the gain. What is the gain? The rate of change, the second derivative of the drain versus the gate source voltage, the drain current, drain source current versus gate source voltage, that ideally in our head, we think that should remain constant, but it's not remaining constant, it's starting to drop. And that is the issue that we are no longer dealing with here with only linear effects, we're also dealing with nonlinear effects. And what is the nonlinear effects? We're starting to deal with the problem that we have voltage-based parasitic capacitances. at the gate, at the drain, at the source, or at the emitter, collector, and base. These parasitics have to be modeled into combination of a small signal performance and into the combination of a large signal performance, have to be modeled into our model so that we can have a description of the drain current that is achievable. And this is usually done by having a characteristic. You have probably seen this a large amount of times now in your cycle of studying electrical engineering. There's the transfer characteristic, output transfer characteristics of a FET, field effect transistor, and then you take certain operating points in the output transfer characteristic. I think you're all familiar with, right? With the cutoff region, with the linear region, with the saturation region, and then you have a compression and breakdown region. And before here, you would have this kind of curve. You would have the current, the drain source current with respect to gate source voltage, and you expect every time you increase the gate source voltage. Now here in the horizontal, you have drain source, obviously, but if you're imagining these steps to be the increase of the gate source voltage, you think in your head, okay, increasing my gate source voltage should increase my drain source current, and my curve should be linear, right? Increasing from lower gate source voltage to more gate source voltage, my curve should just go like that. But obviously, your current curve doesn't just go like this, but your current curve goes has a bit of an S shape, an inclined S shape, and that inclined S shape is the non-linearities that occur when you either have a low driving power, low gate source voltage, or when you have a high gate source voltage or a high driving power. Why the driving power is affecting it? Because remember, we're driving a sinus signal with a certain voltage hoop. The more this voltage hoop increases, the more it pulls your gate at a higher voltage. And also in respect to the BJT, you can have all these parasitic components are also presentable there. And the most important thing is that these parasitic components, you induce a voltage-dependent capacitance in all of these contexts between the emitter collector, emitter base, and base emitter contexts, as well as between the drain source, drain gate, and gate source contacts. You have all the diodes and the respective, parallel to that, you have a diode which restricts a certain flow of current, directional flow, and a variable capacitor, which is variable with respect to the applied voltage, the frequency you're operating at, and the amount of input drive that you give it, the amount of voltage hoop that you're giving into your device. Usually you would expect the device to be like this, to be linear. You know, your device is great, you have a constant gain, and the gain just dies at some point because your device will die. So your device is always the same. I'm giving it 100 dBm, it gives me 120 dBm, and I'm giving it 80 dBm, it gives me 100 dBm, I give it 60 dBm, it gives me 80 dBm, my device is at 20 dB gain, solid, all the way through. But that is obviously not the case. Why it is not solid? Well, the device displays such a non-linearity, a particular feature that is of these devices, and this particular feature introduces then harmonics, meaning that your power is not only focused into one carrier frequency, but your power is also focused into separate in equivalent frequency distance, in equivalent distance in the frequency spectrum, occurring peaks of radiated out power. So you have intermodulations in between your signal. In this part, you will have undesired harmonics. You have your frequency F naught, but then you have your second frequency, you have your third frequency, you have your fourth frequency, your fifth frequency, and so forth. And all of that, what is it doing? Is that instead of me wanting to transmit to you guys at 3 gigahertz a power that is reaching here, if let's say my height is the power, instead of doing this, I'm doing this. And I'm spreading my amount of power that I want to transmit into other bands, and these bands are not good because this band, it could be that the other class is trying to get an information at 6 gigahertz, and I'm transferring something that doesn't interest them at all at 6 gigahertz. And then they receive it, and they might be angry, they might be the police, and they might come and arrest me if I do that. You know, so these nonlinearities occur. Devices are not ideal. They have nonlinear aspects. And these nonlinear aspects, these variable capacitances that are defined, parasitic capacitances, they need to be modeled. And in order to do that, you take the transfer characteristic of such a device and you take it at the operating points. Do you guys remember this, the curve from the short circuit current, the Imax, and the open circuit voltage? Where you move along the curve and you take a certain R optimal, and then on this R optimal you define how much is the hoop of your input voltage, whether it's a complete hoop or where it goes a complete period, or whether the side is only positive and the other side is cut off, and what the effects are with respect to the output. I mean, if you, yeah, so probably given in other lectures, I don't have to introduce that now here, but more operating points are selected, and from these operating points, you try to deduce what are the non-ideal effects of driving a device into saturation, to try to model them into your circuit so that you have a model. And when you have that model, you can put it into ADS and start to design. And behaving non-ideally, so we move on to further on. Now, I think we'll see the non-ideal part again here somewhere. Yes, true. Yeah. Let's move a little bit back. Now, to go back to this topic of, you have a transistor now. You have a model. And the model is this here in the middle there. And you have a transistor. And now you're starting to design a transistor. You're designing this two-port network. A transistor, in this case, is a two-port network. You're adjusting your input matching, you're adjusting output matching. An example of that was last lecture. I showed you ADS, how that looks, schematic window. I showed you in CST how that looks in a 3D EM environment. Go back to the lecture, the video recording, you'll see it in the video recording. In principle, what you have is a series of RLC networks, and or a series of LC networks. The R comes through the fact that you're doing microstrip line and coplanar line. You always have a resistance. You have a certain input-output capacitance and an inductance that comes through it. You're having these two-port devices, and you want these two-port devices to be sequentially put next to each other. So you have a two-port device, you have another two-port device, and you have another two-port device, and this has 5 dB gain, this has 5 dB gain, this has 10 dB gain, and in the end you want to design something that has 20 dB gain. So you put them next to each other. Signal comes in here, gets 5 dB amplified, comes in here, gets 5 dB amplified, comes in here, gets 10 dB amplified. In the end, when you look from the output to the input, you have the signal that came into 0 dB, and you have a signal that came into output and at 20 dB. So you have 20 dB amplification across the device. But in order to be able to put these guys together, you need to be able to decouple the DC part, or you need to be able to decouple the DC sources from in between the devices, because all of these devices will need a DC power. And in all these devices will need to have some connection to the DC source. In order to have that connection, you don't want all of these devices connected to the same, because you don't want the fluctuations. If this device is not the same as this device, it gives you 5 dB, but maybe this device draws 200 milliampere at whatever voltage, at 4 volts, and this device draws 600 milliampere at 2.5 volts or something like that. So you have a different amount of current that has to be driven through the device, meaning that once you connect all of these to your power supply will have major fluctuations. In order to divide this, to decouple this from the DC part, you have these DC, you have these DC decoupling capacitors, these series capacitors. And why are they DC decoupling? Well, for at 0 frequency, they're open circuit for DC, but at higher frequencies, they're just a pass for higher frequency components. Obviously, they have a little bit of loss, because when you process them in a semiconductor technology, they're MIM-capped. Basically, they have a certain microstrip line. Underneath, you have a certain isolator and another microstrip line, and until you reach the end point of your device so that your EM wave spreads around and is transferred to the lower capacitor, the coupling occurs. We'll know what coupling is. The coupling is if your devices are in the near field, the EM waves will couple, will go from one connector to the other, and in between this isolator, you will generate a MIM-cap, metal insulator metal capacitor. and that's why they have a certain loss. But in practice, with lumped components, ideally they don't have, or ideally when talking about the theoretical side, they don't have losses, because for DC they're on open, and for RF, for higher frequencies, they're just a short. Besides that, you don't only need those, but you also need these L's, the shunts, the inductive shunts. Why do you need an inductive shunt? Well, the amplifier, as we learned, is taking input power and is giving you an output power. It's amplifying it via GM. But in order to even reach that, you need to apply a certain bias. You need to give it a certain DC power to reach a certain operating point, so that it has a certain GM, it has a certain amplification, RF amplification, small signal amplification. So you have to apply a large signal voltage to it. And to apply large signal voltage, you can't just, large signal voltage, you can just try to transfer heat power towards the device. It will not have it. So you need some sort of metallic conductor that takes it. And if you have this metallic conductor and it's going to your device, and you're using the Cs to block it off, to decouple it from the other effects from other power sources, you also don't want your RF signal, your small voltage signal to go there. You want your input power and your output power to go along your predefined path. You don't want, because you have some connectors to give it power, to give it DC power, you don't want that your RF power at some point doesn't go to your load, but just goes into your power supply, your DC power supply. So for that, you have these shunts. You have these inductive shunts, which are large inductors, which can be seen here. These large inductors, and these are basically microstrip lines that are meandered and meandered and meandered and meandered. You have a high inductance. Having a higher inductance means that your small wave, your large signal wave, your DC wave will not see any problem with it. It will see loss, but just some millivolt. But your small signal will see a very high impedance. Yeah, basically like that. Yeah. In the sense of no, in the sense of frequency, operating frequency. At the higher frequencies, this will be an open for RF, whereas for DC it will be a short. So not a short, but it will be a normal line. So I have a certain impedance. With that, because what you're wanting to do in the end is that you wanted to have a certain bias point. You apply the certain bias point via these L's and via the inductances or the shunts, and you want to have a matching network to be able to move along in your Smith chart. And I think this is what I've also mentioned last time. This moving along the Smith chart. What does the Smith chart look like? If it's a series L, you move the upper part. This is the Smith chart. Basically, you've all seen the Smith chart by now, and you know how the Smith chart works. The upper part is the inductive part, the lower part is the capacitive part. That's why I also mentioned in the previous lectures always the capacitive part and inductive part. This is defined as that. Why? Because if you have a series inductor, your movement, your transfer of impedance points is as seen in the upper corner. Increasing the series L, you increase the inductive part, you move to the right. Decreasing a series C, you move like that to the C. Decreasing a shunt L, you move to the left of the Smith chart. But always, if you're operating with either series or shunt L's inductances, you are always operating. It always shifts you to the upside, to the upper side of the Smith chart. And if you're operating with capacitors, it always shoves you either positively or negatively, either towards the short or towards the open of the either towards the short is in this direction, I would say, to 0, and then towards the open infinity impedance in the other side. So it always pushes you to the lower part of the Smith chart. That's why the lower part of the Smith chart is the capacitive part of the Smith chart. When you have, for example, a network, a transistor, that is usually in the lower left part. It has a low capacitively loaded input or output impedance. The input impedance can be inductively, that's true, but the output impedance, let's say, is a low, is around 7 plus whatever, 7 minus something J value, an imaginary value. That's in the capacitive part. What you have to do is then to add a bit of inductance. You move them to the inductive part, moves you to with this right movement, right circular movement, and then you add another parallel capacitive part. Why? Because you move from this lower part, you move a bit right. So let's say, what do I have there? Where? Ah, bro. Thank you. Do they move by? They don't move manually. I guess you're seeing it here, right? So you have a Smith chart as is seen there. Huh? You have these like these lines that go like that, and so forth. And then you have the circular lines that extend from here, and so forth. And here you have the reference point of 50 ohm or whatever. And we saw that our input impedance was going like that. Some point like this, and our output impedance was going like that. Here was our starting frequency, here we have infinity, and here we have 0. And here was our end frequency, our F max. Now, we're designing something here, let's say. Now we've said to our customer, oh, we need to our input impedance, or let's say our output, sorry, this was our output. Our output impedance is here. This is what our device gives us. I don't know, it could be, if this is 10, this could be something like J minus 7, sorry, like something like 8. Aha, this is how it works, okay. Now I just have to know how it goes the other way. Now I see. It's good? Okay. Let's say you're having here 8 minus 20J or whatever. You know, some impedance. And you know that in order to transfer the ideal output power to this, you'll have to have the complex conjugate. So you have to go to 8 plus 20J to have the full amount of power transfer. And where is 8 plus 20J in a Smith chart here? Where is 8 plus 20J? Here, right? Somewhere here. Somewhere here. So you want to reach this point. Well, how do you reach this point to this point? Well, you can see, oh, I need to do a matching network. What is a matching network? A matching network is a series of LCs. So there's a series of an L, and a series of a parallel C, and then a series of an L, and a series of parallel C. And how you do these parallel Cs, if you do them as stubs or as min caps or whatever, and how do you do these Ls? You know, that is your it's a filter. It's basically a filter. That's your decision, right? So then you want to move from here, you want to move to this point there. In order to move to that point there, you have to look, what does it do? Well, if I do an L, if I do a series L, I will be able to move in this direction. So, I mean, this is a very unfavorable position, but let's say we're trying to move there. You would be, it's a very unfavorable position. Let's say we're in this position here. Let's just ignore this part. Let's say we're in this position here. The ideal, and then our matching is here, so that complex conjugate. So in order to move there, we would, or technically sometimes you won't be able to move, as is here the case, or was here the case, you won't be able to move directly to your complex conjugate. That's why you don't have always the full power transfer, you have losses. But you can move somewhere in this area. And how do you do that? Is by adding an inductance. A series inductance, increasing a series inductance, you add some line, you add some microstrip line, just to the output of your amplifier, you add some microstrip line. You have this amplifier we saw with the gates and with the drains here, and then with the sources that were combined to each other, you know. To this, you add the microstrip line, just like that. And adding the microstrip line increases you towards so you don't go directly to the complex conjugate. It's very difficult to reach the complex conjugate directly. But you go in some area close to the complex conjugate. As closer you are to the complex conjugate, as better you have a ratio of transferring your power. So you're here, which is great. But then you notice, oh shit, so we're here. Just erase this basically. And then you notice that, fuck, oh shit, my device doesn't have the required gain. Right? I need another device here. You know, it's waiting, gain 1, and gain 2 is waiting here. So, well, how do I do that? I'm here, and I need to reach there. And this device, the vendor said, oh, this is 50 ohms, buddy. Yeah? He sold it me. So then I have to start. I'm here. I'm thinking like, oh, damn, what do I do? Well, I increase a parallel capacitor, and what does that do? It shoves me down here. And then I'm here. And then what I think about there is like, oh, here's 25 ohm. Yeah, it's close enough. I probably have a VSWR of 2 to 1 or something like that. But I obviously can do better. And so I have this first component, this is my second component. So what do? I add another L. And I move like that, whoop, up here. Usually it's at the opposite side. So you would move smaller here. You would move like that would be happening. The span, it's also measured. There's like waves taken like that, and this is like measures your how far you're moving your transitions. And these transitions, the further they are, the more they restrict your bandwidth. So the more you jump, if you jump like that, and then you come back here, it is not the same as jumping up here and coming back here, because it reduces the amount of bandwidth that you can apply from the device. But anyway, that's something for another matter. So we're here, we moved to here, and then we came back here, and now we made another jump with our C, and now when we're here, we're quite close to the 50 ohm, but not exactly close. That's why we add another C. And when we add another C, we're reaching this 50 ohms part. But before we forget this, before even connecting it here, we have a problem. Because this thing has its own gate source and drain source. And you don't know this. You don't know how this will change with temperature, how much the drain current will change. You don't want the fluctuations here. If the voltage drops here, and the current increases here, and the voltage doesn't change here, but you don't want the current to increase because your device might get damaged. So beforehand, you have to apply a decoupling capacitor. And here, once your RF, your small signal, has entered through here, because it's a short circuit for the small signal, you don't want your small signal to go up here. So that's why you have a shunt, you have an inductor, and this inductor for high frequency signals will be as if it's an open. And this you can realize by having a microstrip line. It goes like that, it goes like that, it goes like, and then through a air bridge, you call these air bridge wave process goes into the other conductor. So you have one conductor here, then you have a long meandering microstrip line, because you know, if I'm not making any mistakes now, any microstrip line will have an inductive component, it will have a resistive component, and it will have a certain output and input C. Something like that. A certain capacitance. And this can be neglected when this is more or less neglected, can be neglected, but the main parts are the inductance and the resistance of the line that you apply. So the thickness of the line and how wide the line is and how long the line is. The length will define the inductance, and the width will define what kind of resistance it is. 50 ohm, 75 ohm line is.
By adding this decoupling capacitor, aren't we just also moving our S point in this case?
Ah, you mean? No,
No,
because we're operating here at 50 gigahertz or something like that. This will only affect, this capacitor here is small enough that it will only affect the cutoff frequency is really, if this is the frequency part, it is something like that. So yeah, something like if it's 1 and here is 0. So here it is very low. It's in kilohertz region or something like that. So it's you don't in terms of RF you will not see this unless you make it huge, and then probably you at some point you will see it. Okay, I can't believe it. So, okay, a little bit fear that would crash. how you realize then these components, how you realize these transmission line components, either by transmission line or by stubs is of your own choosing. Now, what you I think beforehand probably had is stubs, open stubs, short circuit stubs. Do you guys have you had that? Okay, so you know that this lambda quarter transformation is very important. How long the wave travels through the device. As you can see, this how long the wave travels through a conductor. That is antennas, that's in matching, in filters, and everything. The amount how this is related to that, and then you can realize these transformation networks with such open and short circuit stubs. And if you do that, then you can define, when you characterize the device, as we said, the MSG and MAG, when you have that kind of from your vendor, you have the MSG and MAG, you have the where your device is stable and where it is unstable. You have this plot. Then here, then you can also plot in the same way. If you have a transistor model, you can also plot in the transistor model where that transistor would go beyond these stable points. So you can plot via this K factor, and knowing having this information from your vendor, from the person who produces this technology, you can calculate circles of impedance circles where your input and output at what frequency points, at what frequency and what impedance points the performance will be stable. Their device will be unconditionally stable. In which areas? And when you have these areas, so you have a smaller circuit for the input and a larger circuit for the output where your device is stable, in that cross section, you try to hit the impedance points, because in that cross section, because obviously your input and output are talking to each other. In that cross section, you'll be able to have the respective impedance points where your device will be stable, your transistor will be stable. So you're trying to have the input and output, the input load, the input matching, the input source, the source driving your device, and the output load matching to have within these circles of stability circles of stability where your device will be stable. These stability circles can be calculated as can be seen in the formula above. If they're below 1, or if they're above 1 if they're below 1 for the input and output reflection coefficient, then you're within your stability within the stability circles, and if you're within the stability circle, you're in the stable case. So it's more depicted here. So where that region is, and if that region aligns with each other. I think biasing. Yeah.
We said that this parallel of frequency, whatever is lying, it's
stable. But it's also dependent on It's also dependent on what your load and what your source impedance are, because your device is not, there's a crosstalk from your output to your input. Your device is not the input is shut away from the output. There's a crosstalk from your device output to your device input. Anyway, I see that we're running a bit low on time, so I think we'll stop the lecture here, and we'll continue from this point to the next lecture. If you have any questions, we'll do them after the recording. Otherwise, thank you very much for being here.